All right, so we're right here. We're going to talk about quantum model. So electrons behave as waves, and they also behave as particles. So they have some physics that are involved with each. So electrons have wave-like properties. I talked about that when we were talking about the electromagnetic spectrum. Consider the electron as a wave confined in a space that can only have certain frequencies. So that would be like the energy level, the sublevel and orbital where they're confined to, and it's based off of their energy, which would in turn be related to their frequency. The Heisenberg uncertainty principle states that it's impossible to determine at the same time the position and velocity of an electron or any other very small particle. So we've been drawing it, and when we draw our Bohr models, like we know exactly where the electrons are located, but in truth, we just know the probability of where they're located. Our electrons are located by their interaction with photons. Electrons and photons have similar energies. So when they interact, the photon will knock the electron off of its course, and then that is how it can kind of be located. The Schrödinger, that was the scientist's wave equation, which is a very complex equation that we will not be actually doing, proved the quantumization of electron energies and is the basis for the quantum theory, which is the atomic theory that holds true at this point in time. The quantum theory describes mathematically, so we're talking statistically, the wave properties of electrons and other very small particles. Electrons do not move around the nucleus in a planetary orbit like we've been drawing them with Bohr models. And hopefully if you watched the video, you saw that last night. So electrons exist in regions called orbitals. And an orbital is a 3D or three-dimensional region around the nucleus that indicates the probable location of an electron. Remember, we're just doing this with a mathematical formula, so we don't truly know the exact location. We can just give up the probability of it. The Schrödinger equation gives a probability of a single electron being found along a single x-axis. So quantum numbers are how can be assigned to an electron in an element. So quantum numbers specify the properties of atomic orbitals and the properties of the electrons in those orbitals. So there are 4 quantum numbers. 4 quantum numbers will give the location of an electron in an element, and no 2 electrons have the same quantum number. So the quantum numbers, we have the principal quantum number, we have the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. And they get more specific as you go down. So if we talk about the principal quantum number, there could be several, if not more, electrons that could have that same principal quantum number. But when we finally get down to the very last one, there would only be 1 electron that could have that one. It's kind of like if you were lucky enough to go see the Astros last night. The principal quantum number would be like that you went to Minute Maid Park And then the next one, you had to find your section. And then we get more specific. You had to find your row. And finally, you had to find your seat. And nobody should come and sit on top of you. There should just be one person in the seat. So that's what we're looking at here. They get more specific as we go to each quantum number. So the broadest one is the principal quantum number, represented with a little n. Excuse me. And it indicates the energy level and size of the orbital that is occupied by the electron. So as you increase the principal quantum number, so I might increase my number, right there, it's going to increase the size of the orbital and the energy. So when we've been drawing our Bohr models and we've been doing a nucleus and then the different levels around it, those are what would be considered a energy level. That's what we're talking about here. Although we're finding out as we move through this unit, if you watch the video, that it's not that simple. Values of n of your principal quantum number are always positive integers. So you could have a possible n equal to 1, 2, 3, 4, and then you could go on. Right now, the highest energy level that electrons are in this periodic table would be energy level 7. The N1 is closest to the nucleus. It's going to be the smallest, and it's going to be the lowest in energy. So it's going to be where an electron wants to go and fill in first. The number of orbitals possible per energy level or energy shell is equal to n squared. And we'll go over that again in a minute, but that's kind of a helpful, these little n's and how they're related to each other can be very helpful as we do these different configurations. The next one is my angular momentum quantum number, represented by a small l. It indicates the shape of the orbital and the energy sublevel. The number of orbitals, orbital shapes in a specific energy level is equal to n. So if I'm at energy level 1, I'm only going to have one shape of orbital. Possible values are equal to 0, 1, 2, 3, or 4. The shapes are designated by S, P, D, and F. These are sublevels. And that S, P, D, and F is what we'll be using during electron configuration. So S is just a spherical shape, and it has a angular momentum quantum number. So its a value is equal to 0. P is dumbbell shaped, or you get our figure 8. It has a value of 1. A D sublevel has a value of 2. And an F sublevel has a value equal to 3. We don't talk about that D and F shapes because they're really complex. So you can't just say they're spherical or dumbbell shaped. All right, the next one that we have is our what's called the magnetic quantum number. And it tells you the orientation of the orbital around the nucleus. And all of these, if you would change all those orbitals to sublevels, I'm going to just put SL. I'm going to say SL is equal to sublevel. So the S sublevel only has one possible orientation. And that one possible orientation is equal to 0. And we would show that orientation with just one line. When we're doing electron configuration, a line represents an orbital. So P sublevel has 3 possible values. So we would draw 3 orbitals. A D sublevel has 5. So when we start drawing these, we'll be drawing 5. And then an F sublevel has 7 possible orientations. So we would draw 7 lines because it has 7 orbitals, 7 possible orbitals, or 7 different orientations. And the way that these work, and I'll show you on the F, these are the values that are possible. You start with the 0 in the middle one. It's like a time, not a timeline. It's like a number line. So this orbital has a value of 0. This is 1, 2, and 3. And then on this side, it's -1, -2, and -3. So far we have our energy level, which is N. Oh, thank you, ma'am. So this is going to be my broadest. Then from there, we have our sublevel, getting more specific, which would be represented by L. Then within the sublevel, we have orbitals. Those are represented by M1. And then finally, we're going to have the spin, which is our last one, and it's represented by M with the little s. So it starts broadest up here, and then it gets more specific. So my spin is going to be my most specific. So by the time I assign an electron, an energy level, a sublevel, and an orbital, at that point, there's only 2 electrons that can have that. And one of them will have 1 spin, and one of them will have the opposite spin. All right, I'm gonna move this up a little bit. We're good. All right. So last one is the spin quantum number. And remember, we're trying to put 2 electrons in an orbital, and they're both negative. So they're trying to do something to separate themselves. So that means that they're going to spin in opposite directions. So the spin quantum number indicates the spin state of an electron in any orbital, and it only has 2 possible values. A single orbital can hold 2 electrons, which must have opposite spins. So let's say that I'm going to do as S sublevel. It can only have 1 orbital, so it'll only have 1 line. In that orbital, it can have 2 electrons with opposite spins. So we're going to let arrows represent electrons, and one will go up and one will go down. To show their opposite spins. So that would be our 4 quantum numbers. So one of these would be a plus half, and one of them would have a minus half value. All right, so this little box comes in handy because it kind of just relates to different things. So principal quantum number, the broadest one, is going to have a value of N. The sublevels that would be in any main energy is also equal to N. So in other words, if I'm in energy level 3, that means I should have 3 sublevels in that energy level. The number of orbitals per sublevel, we said each sublevel can hold a different number of orbitals. If you notice, a S is always 1, a P is always 3, a D is always 5, and F is always 7. That doesn't matter what energy level they're in. That always is going to be the same. The number of electrons per sublevel are going to be 2 per orbital. So we said at S sublevel, has only ever one orbital, so it would have 2 electrons. To get how many electrons in you as if blah, blah, that you have in a total energy level, you're going to use that 2n squared. So let's just do an example. If I'm in energy level 3, so let's say I'm in energy level 3, then I should have 3 sublevels. And to find my total number of electrons, I'm going to do 2 times 3 squared. So 3 squared is 9, 9 times 2 is 18. So that means if I fill up energy level 3, it would take 18 electrons to fill that totally up. Because the square takes into account that each orbital can hold 2 electrons. And the last little thing we're going to look at is just some rules that will affect us tomorrow as we start our electron configuration. Oh no, I forgot this little box. Let's fill this in. This one comes in handy. So I'm going to have to draw outside the box at the top because I write too big. Y'all might be able to fit yours in. In the first box, it should be energy level, or you could put just EL. And I'm going to put a parentheses of 7 because right now that's how many energy levels we have elements for. The next box should be your sublevels. And there are 4 of those. S, P, D, and F. Those are my sublevels. And S sublevel only has room for 1 orbital. P's always have room for 3 orbitals. D's always have room for 5 orbitals, and F's always have room for 7 orbitals. That doesn't matter what energy level they're in. Those sublevels always will have that number of orbitals. Each orbital can hold 2 electrons, so that means an S can hold a total of 2 electrons, a P total of 6 electrons, a D total of 10 electrons, and F finally 14 electrons. That's the maximum number they can hold. And like I said, these numbers, it'll become more familiar over the next couple of days. All right, now let's fill in those last couple of little things on this side. Just some rules that govern electron configuration. The first one is the Pauli exclusion principle. It says no 2 electrons in the same atom can have the same set of 4 quantum numbers. So I already mentioned that a little bit earlier. The next one is Hund's rule. It says orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. So if we look at a P sublevel, we said it can have 3 orbitals. If electrons were to fill that up, there's going to be 1 electron in each orbital before it doubles up. And once again, that's because everything's negative, so they're trying to get it far apart as possible. Kind of like if y'all do a school trip, try to get your own bus seat before you have to double up usually. And the last one is Aufbau, AUF-BAU principle. It just says an electron occupies the lowest energy orbital that it can receive. And I've kind of talked about that a little bit already, and then it's going to guide how we do our electron configuration because they're always going to want to go into the lowest one first. All right, if you will get out your Chromebook and go down to references. There is a periodic table for you to color, make your own. I can find mine. Maybe I don't need a question. I guess. All right. If you go all the way down to references. There's that one. Well, light. Open up the one that says electron configuration, periodic table for electron configuration. Okay, and you're going to want to get your periodic table so it looks similar to this. This is a periodic table that will help you with electron configuration. So it's important that you get where the S block is, where the D block is, P block. Notice that helium is part of the S block. You could put in every element if you wanted to. I just put in some elements here and there to help me find where the boxes are. Also put like a little cheat sheet over here that told me how many sublevels each, I'm sorry, how many orbitals each sublevel has. So I know that you will not get through with that today. So I would recommend you do it at home. It'll be a useful tool for you. I do have some markers up there if you want to grab some, and some highlighters if you get to that point where you're ready to color. And then this will be yours to use when you do your practice or quiz or test, and it helps out a lot. So no quiz tomorrow. Please do watch the video tonight, and then quiz on Friday.